Record on this computer. Okay. Let me move some of these things around on my desk here. Let's see. I'm not quite sure how far back I should go in describing things here. Well, maybe I'll just sort of zip through it just at a faster rate. I guess we don't need this to be quite so big. So general coordinate transformations, again, one-to-one smooth. So there's no issue of singularities or differentiating. Of course, that's what we think of as a general coordinate transformation. But in any particular problem, one might be forced to change coordinates in a way that does have a singularity, and in that case, one has to rethink things. So you can't just assume that everything is smooth and one-to-one. It's rather that if things are smooth and one-to-one, then we basically have no problems and can continue. Now, tensors are quantities that change simply under general coordinate transformations. And of course, the simplest thing is for something that doesn't change at all. A quantity that depends upon space-time is called a field. The second simplest kinds of tensors are the vectors, which can be either covariant, that is to say, ones that transform like the derivative of a scalar, or contravariant vectors, which are ones that transform like the differentials of a coordinate. And of course, we're trying to avoid having to have too many sum signs, and so we have we're following Einstein's summation convention. The way he introduced it originally was that if you had one lower index and one upper index in the same expression, then by that is meant the same monomial, then you sum over it. So in other words, in this equation here, you sum over it. But on the other hand, if you have here, oh God, what is this? Is some trick that I have to do to get this to start? I mean, the pencil is certainly charged. So I'm tap to connect. So I've tapped to connect. Boy, I don't. All right, let me try this one more time. I tap to connect. And now I'm going to go over here. Okay, so let me just go to something like this. Okay, blue. All right, so in other words, if we have something of the form A times a covariant vector AK plus B times a covariant vector BK, we don't sum over K in this case. In fact, this is actually an equation that makes very little sense, because it would have one part of the equation transforming covariantly and the other part transforming contravariantly. So this is kind of funny. So it's when the index is repeated in the same monomial, and a monomial means things that are multiplied together without any plus signs. So you have an upper L, a lower L, an upper M, a lower M, a lower N, an upper N. You sum over L, M, and N. And these, the original Einstein equations in one coordinate system look like this. You then transform, you then transform them to another coordinate system, and then they wind up looking like this, where this whole equation is equal to this multiplied into that equation and summed over I and K. The basic invariant of general relativity is what's called the invariant distance, or the line element, or the interval. There are all kinds of different names for this thing, but it's GIK dxi dxk. It's the thing that's invariant. In special relativity, the thing that's invariant is dx squared minus c squared dt squared. This is the thing that's invariant in special relativity. And in general relativity, but of course there you can only have, so this is invariant under Lorentz transformations. Whereas in general relativity, what you have is ds squared equal to GIK dxi dxk. So this is invariant under general coordinate transformations. Okay, so that's a big change, and the role of GIK is to make this possible. And what GIK then describes is it describes our space-time. And one way to think about it is to imagine the points of our space-time as being real physical things that we are describing with different coordinate systems, but we're describing the same surface with different coordinates. And so the points of the surface are scalars. They're invariant under changes of coordinates. And the difference, on the other hand, between 2 points that are close by is then a scalar, because it's the difference between 2 physical points, difference of 2 scalars. Scalar in the sense of being invariant under general coordinate transformations. And then these points then are, or if you think about it, a point, after all, is just a point. It's not a vector, is it? Anyway, when you change the point, how does the point change? Well, it changes by the derivatives of a scalar times the covariant differentials. Well, this is something that is a scalar, because this is a covariant vector and this is a contravariant vector. Now I'm using the wrong thing to raise these vectors EI are tangent vectors. They're tangent to our physical space-time, and the inner product of 2 tangent vectors is the metric of space-time. So EI dot EK is that metric. And what is this zeta? This zeta is it's the metric, it's the flat metric of the embedding space. In other words, our curved space-time is embedded in a flat, higher dimensional space-time. And so zeta is equal to something that might have a couple of minus signs and then at least 3 plus signs, maybe more plus signs, and conceivably even more minus signs. So let me stick another minus sign there. So that's a pretty generous zeta. And so the general expression looks like this. This is called semi-Euclidean. If it were all plus signs, it would be called Euclidean. And in fact, that in that case, we'd be talking about a Riemann manifold. But here, since we have to have these time-like dimensions, then we have some minus signs, some plus signs, and everything over here, of course, is zero. So we have a lot of zeros here. And so forth. For example, the surface of a sphere is naturally embedded in three-dimensional space. In three-dimensional space, the metric zeta is just the identity matrix. In the three standard cosmologies, Robinson-Walker cosmologies, one is just Minkowski space, in other words, flat space where zeta is just minus 1, 1, 1, 1. And in fact, G is very simple. G is just equal to minus C squared and then A effectively, where A is this expanding space, expanding scale factor. The open and closed Robinson-Walker metrics have 5-dimensional zetas, and the closed universe has 4 space dimensions, 1 time, and the open one has 2 time dimensions, 3 space dimensions. The squared separation between 2 points that are nearby is given by the change in the point dotted into the change of the points. These are these tangent vectors dotted into each other, and the dot product of the tangent vectors using this as the metric to do the dot product is the metric of spacetime. So that's how things go. Common notation is an economical notation. Whether it's better than this notation or that notation, I don't know. You guys should send me some email and say what you think. I can switch. I don't have a dog in this fight. I'm trying to get the chat thing going here. Okay, so there's the chat window. So anyway, there are these, the derivative of a tensor, or double derivative of a tensor. We can write it this way, we can write it this way, or can write it a comma ik. So this is obviously more economical. Whether it's better or not, I don't know. In terms of the compact notation, the invariant dp squared or ds squared is p comma I dxi dotted into p comma k dxk, and that's ei dot ek dxi dxk, and that's gij dxi dxk. And this is normally written as ds squared rather than dp squared. And if you have a derivative with respect to a primed coordinate, well, for example, the derivative of xk with respect to x prime I looks like this. I thought I'd do 2 examples that might make this stuff look I don't know, more familiar, simpler, or anyway, in spherical or polar coordinates, a point on a 2-dimensional surface of a sphere, radius r. Well, you guys all know this. You can probably write it down faster than I can. The point in XYZ coordinates is r, sine theta, cosine phi, sine theta, sine phi, cosine theta. And that's in this embedding space. If I switch here to something like this, then we have this polar angle theta, and this goes down to a point here, and there's the x, there's the y, and the point here has a z that's essentially there. So this is the x, that's the y, that's the z, and they're given by these coordinates here. So that's the angle theta. The tangent space, E2 is just the plane. So the tangent space at the point is spanned by the vectors that are E in the theta direction and E in the phi direction. They're just the partial derivatives of theta and phi in these two directions. And this way you just differentiate with respect to theta and you get that, and differentiate with respect to phi and you get this. So you just get minus sine phi here times sine theta, and then cosine phi times sine theta when you take the phi derivative of this. And when you take the dot product of these with respect to the standard, I forgot to write down what zeta is here. So here zeta is obviously, here zeta is equal to just 1, 1, 1. Diagonal 1, 1, 1. In other words, so let me stick in diag. In other words, this is equal to 1, 1, 1. Just the three-dimensional identity matrix. That's how you take the dot product of these vectors. And so the dot product of E theta with itself is cosine squared of theta times cosine squared of phi plus sine squared of phi plus sine squared of theta. That altogether is 1, so you just get r squared. The other hand, down here, you get sine squared times sine squared phi plus cosine squared phi, and so that just leaves you with sine squared theta. The determinant of this is then r to the 4th sine squared theta, and since these vectors E theta and phi are perpendicular, the infinitesimal distance dp squared or ds squared is just this squared, and that turns out to be r squared d theta squared plus r squared sine squared theta d phi squared. This sphere, you will not be surprised to hear that it is a maximally symmetric space. I mean, what could be more symmetric than a sphere? Well, there's something that's equally symmetric, and that is the hyperboloid. If we embed it in a three-dimensional semi-Euclidean space with a funny metric, and the funny metric is that zeta is minus 1, 1, 1. So in this case, we have the surface of the hyperboloid has coordinates like this, and the tangent vectors then are the derivatives of this point with respect to theta and phi, and the derivative of cosh is sinh, derivative of sinh is cosh. And then over here, you take the phi derivative, and so you get minus sine, and then you get cosine. And so that's what you have. But now when you take the inner products, you have to use this zeta metric. And so E theta dot E theta is minus sinh squared times cosh squared and or cosh squared minus sinh squared. That's 1 times r squared, so it's just r squared. These two are perpendicular, and E phi dot E phi is just the dot product of these, and since the zeta is just 1, 1 in these two directions, there aren't any you just get sinh squared, in other words. This x effectively is a time dimension in this case. And so the space-time metric then is r squared sinh squared, and ds squared or dp squared is r squared d theta squared plus r squared sinh squared theta d phi squared. So the hyperboloid has the symmetries of the Lorentz group in 1 time and 2 space dimensions, and it's one of 3 maximally symmetric 2-dimensional spaces. The other 2 are the sphere, which we just looked at, and just the plane, which is the plain old plane. If you instead used not zeta equal to -1, 1, 1, but wanted to have this hyperboloid embedded in ordinary physical 3 space rather than in a space of 1 time and 2 spaces, you would then have something that would not be maximally symmetric. And in fact, you know that in 3 dimensions, a hyperboloid, well, it would look something like this. Something like that. And that's not maximally symmetric because the z direction and the xy directions are different. There's another hyperboloid that you can make that looks like this and like that. And this continues. I'm just sort of drawing. Looks like this. So the real hyperboloid looks like that. Well, I guess I've kind of screwed this thing up by overly drawing it. Anyway, neither hyperboloid, when embedded in ordinary 3-dimensional physical space, is maximally symmetric. We've already gone through the quotient theorem. The quotient theorem is just a way of checking or being sure that or proving that a given quantity with various indexes is actually a tensor. And when would it be a tensor, or what does it need to be like to be a tensor? Well, it has to transform simply as possible under general coordinate transformations, and then it'll be a tensor, and in fact it's sufficient for for the product of this unknown quantity with a given tensor to transform as you want it to transform, and if it does, then the original thing you were looking at is a tensor. Well, we went through that a couple of times, so I'm going to skip it this time. The inverse of the metric tensor, the metric of spacetime is a non-singular metric because this thing here, gik dxk, can't vanish unless all the dx's are 0, because if it did, then the difference, the 2 points would be identical or have no separation, even though their coordinates are different, and that would be pretty crazy. So G is non-singular, and it has an inverse, and the inverse satisfies these conditions in all coordinate systems. The inverse metric is a rank 2 contravariant because the metric is a rank 2 covariant tensor. I think we can skip that proof. The dual vectors are dual to the tangent vectors. They're also called cotangent vectors. As usual, you can, the way you get a cotangent vector is you use the inverse metric to raise the index of the tangent vector. And you can also, if you have a cotangent vector, you can use the metric of space-time to lower the index of the cotangent vector and get yourself a tangent vector. The dot product of 2 cotangent vectors is then a the inverse metric, just as the dot product of two tangent vectors is the metric with two lower indices. And let's see, why do I have this equation twice? All right, well, that's pretty silly. I don't know why I have that twice. Anyway, it may be that I brought this, I added this to the class notes just last night or the night before. The idea is that the outer product of a cotangent vector with a tangent vector, or equivalent, well, a tangent vector with a cotangent vector, or a cotangent vector with a tangent vector, is the identity matrix of the tangent space. I actually went on, I Googled outer products and found that apparently one notation for outer products is this circle with a cross. And so this is effectively an outer product. So if you sum over the cotangent, the outer products of the tangent with the cotangent vectors, you get something that's the identity vector, identity matrix in the space. And the reason for that, the sense of that is that P that this thing, I'm calling it P, on a tangent vector where you have then EK dot EI, and this is delta KI, and so this gives us back EI. Notice, though, that when you take this inner product, you're using zeta, you're using the internal metric. Anyhow, P on a cotangent vector is also a cotangent vector, and and so one way of writing P, well, it's the identity matrix, as I just said. We went through this, but it wouldn't hurt, I guess, to say it again. The covariant derivatives of contravariant vector, well, you want something that transforms like a mixed tensor. And so the best thing to do is to make a scalar by taking by multiplying VI with a tangent vector and summing. And then we know if we take the ordinary derivative, we get a covariant vector. And but then when we take that derivative, we get something that's actually a vector, and a vector in the embedding space. And what we want is just something that's doesn't refer to the embedding space at all. And so we take a dot product with the cotangent vectors, and that gives us delta Ki and Ek dotted EIL. And that then is something that's called the affine connection or the Christoffel symbol. So the covariant derivative of a contravariant vector is the ordinary derivative, or let's say the kth component of the lth covariant derivative, or the lth covariant derivative of the kth component of a contravariant vector is the lth ordinary derivative of the kth component of the contravariant vector plus the ith component of the contravariant vector multiplied by the Christoffel symbol of the second kind, gamma KIL, or gamma KIL is the inner product of the cotangent vector ek with the nth derivative of the ith tangent vector. And that's often written as a semicolon, so one gets a formula like that. And the nth derivative of the Kronecker delta is obviously 0, because the Kronecker delta is either 0 or 1. And when you differentiate, and the Kronecker delta can be written as the dot product of ek with ei. And when you differentiate that, you get these two expressions. And so you can then, and then if you use this identity here, you then see that the covariant derivative of a cotangent vector is the ordinary derivative plus, this is the Christoffel symbol, but multiplied by the ith component of E. And you can then rewrite this as using that Kronecker delta identity. Rewrite it this way. This is the identity, and so this just gives us 1, and so we have EKL, the nth derivative of EK minus itself equals 0. So the cotangent derivative, cotangent vectors have no covariant, have 0 covariant derivatives. If we now want to do the covariant derivatives of covariant vectors, we form a scalar like this. We take its derivative and we have something that's a covariant vector, but to get it to get it in a form that doesn't refer to things that are outside they're in the embedding space, we take the dot product with a tangent vector. And so the nth covariant derivative of the ith component of a covariant vector is, which can be written as a semicolon, vi semicolon L, is ei dot the nth derivative of v, and that is then these terms. And then the ei dotted in to ek is a Kronecker delta. This is something that is related. This is minus that, and that is a Christoffel symbol. And so the rule for covariant derivatives of covariant vectors is ordinary derivative, and then a minus sign, a Christoffel symbol, and the vector. Notice if you use the semicolon and comma notations, then you have I semicolon L is I comma L minus gamma upper K lower IL VK. So that's an advantage of the comma and semicolon notation. But of course, if you get the order wrong here, it doesn't matter, because gamma in standard general relativity is symmetric in its lower indexes or indices. And if you take now the covariant derivative of a tangent vector, you then wind up with this expression here, and this thing is the identity, and so you get 0 again. Covariant derivatives of tensors. In this way, what you do is tensors, of course, transform like products of vectors, and the trick here is, well, how would you get the covariant? How would you define the covariant derivative of the product of two contravariant vectors, AI and VK? Well, one way to say that is to think like Leibniz and say, well, we want something that transforms with two like a tensor of rank 3 with 2 contravariant indexes and 1 covariant index. And one way of getting that automatically is to say, well, if we take the covariant derivative of one of the contravariant vectors and multiply it by the other contravariant vector, we have something that is a tensor of rank 3 with the appropriate indexes. And then if we also take AI times the covariant derivative of the second contravariant vector, we also have something that is a tensor of rank 3 with the right properties. And moreover, it satisfies the generalized Leibniz rule, which is that the derivative acting on the product is the derivative acting on the first element times the second plus the first element times the derivative acting on the second. Mathematicians call something that does this, they call it a derivation. And anyway, what the point is that this works because it gives you something that transforms correctly. And so if you have a tensor that's rank 2 contravariant and you do the same thing, you're going to get something that transforms correctly. In other words, this combination, the ordinary derivative plus two terms with two different Christoffel symbols gives you something that transforms correctly and is an appropriate derivative. And if we think about the product of a contravariant vector with a covariant vector, and we do the covariant derivative of that in a Leibnizy way, then we would take then the covariant derivative of the first vector times the second plus the first vector times the covariant derivative of the second. This will transform, each of these transforms correctly, transforms like a tensor with the right indices. And because we have both of them, though, we have the right derivative structure. And so if you then go through the details and remember that the covariant derivative of a covariant vector has a minus sign and a gamma, you then get this structure here. And so the covariant derivative of a mixed tensor looks like this. And again, transforms like a rank 3 tensor. So with two covariant indices and one contravariant index. And the covariant derivative of two covariant vectors, well, it's dl on these two guys, and so that's going to be dl on ai times bk plus ai times dl on bk. And if you work it through, you get this. So that this is the general expression then for the covariant derivative of a rank 3 covariant tensor. Okay, so now I'm going to switch to well, this is something that I mentioned last time. Let me make it bigger. Covariant curls. And so suppose you take a covariant derivative of a covariant vector, but do it in an antisymmetric way. What happens is that because this thing is also called it's called an affine connection or a connection, and affine just means something that relates to points that are close to each other. Anyway, the Christoffel symbols in standard relativity are symmetric in the lower indexes, and so these two terms, because of the antisymmetry, cancel, and you just get the ordinary curl. So that's why this thing that Faraday and Maxwell invented. In fact, I think Heaviside had something to do with after Faraday and Maxwell had discovered everything. Heaviside wrote it up in a nicer notation, the modern notation, Anyway, this thing is antisymmetric, and it's then a generally covariant, second-rank covariant tensor. And so that's what happens when you discover really fundamental physics. It takes a form that reflects symmetries that you didn't know about, because the true theory of physics is very, very symmetrical. Well, anyway, that's more philosophy than science. So the general covariant derivative of a covariant second-rank tensor looks like this. We just sort of went through that. If the original tensor is antisymmetric, then it turns out that if you add together three cyclic permutations, you get zero. No, you don't get zero, but all the Christoffel symbols cancel. So they're canceling because the Christoffel symbols have this symmetry, and because the tensor, the rank 2 covariant tensor is antisymmetric. So the sum, the cyclic sum, ILK, KIL, LKI, sum together, you write the three of them down, and the Christoffel symbols all cancel. And what you get there in particular is the homogeneous Maxwell equations. And so what do we find? That the homogeneous Maxwell equations then are tensor equations valid in all coordinate systems. The next topic is parallel transport. And the idea here is, in fact, let's do the example first rather than and let me follow the example carefully so that I don't get things screwed up, and then I can illustrate it. So we're going to parallel transport a vector up from the equator along the line phi equals 0. So let me go to, all right, so I'm going to write sort of the z-axis, the x-axis, the y-axis, and then we imagine we have a sphere. And so the sphere looks something, the surface of the sphere looks something like this, and it goes around like that sort of, and then there's looks somewhat like that. Okay, well, I've not done this quite right, but anyway. So let's parallel transport a vector, and it's going to be a vector in the phi direction, which points in the y direction initially, up from the equator along the line phi equals 0. So this vector phi points this way, and we're going to move it up like this. This is what's called parallel transport. And what happens when we get to the top? When we get to the top, this vector is pointing this way, but that's the same as the theta vector. That's the same as E theta. And now if we parallel transport, so I'm going to write it as a red line. And now if we parallel transport E theta down, what we get is something like this, where and this looks like, I hope I did this right, by the way. Right. Now we parallel transport E theta down to the XY plane. And when it reaches the equator, it's pointing in the minus Z direction. And so then if we parallel transport this along the line, along the circumference of the sphere, we find that we've got something that's perpendicular to the vector we started with. And this is due to the curvature of the sphere. So this is an example or an illustration of parallel transport. It's an illustration that I wish I had in my book, but we don't have color, and I didn't take the time to use MATLAB or Python or something to do a really nice picture. So let's look at the thing more formally and more generally and less pictorially. So what we're doing is we're thinking of the movement of a vector along a curve on a manifold. Manifold just means surface. On a manifold so that its length and direction in successive tangent spaces don't change. So let's see how we express that mathematically. So you have a vector which is components vk, tangent vector ek, or covariant components. This is actually a scalar here, ek, because it's in the sense of invariant. So it's v covariant, kth components of the kth covariant component of v, and the kth cotangent vector. Anyway, in parallel transport, the vector can change, but the projection of the change into the tangent space must vanish. So dv dotted into the tangent space has to vanish. And so in terms of contravariant components, what we have then is that E upper I dotted into dv, and dv is v partial L dxl. So this is the change in this thing, dxl, and we're differentiating this. See, I was imagining, let me just remember, let's go back to the example. In this example, I imagined the sphere embedded in 3 space. And so all these vectors, these blue, red, and green vectors were all tangent vectors. Well, anyway, so what are we saying here? We're saying that EI dotted into this times DL, this should vanish. And differentiating, we get 2 expressions here. EI dot EK is just a Kronecker delta, but then EI dotted into this, that's a Christoffel symbol. So the statement is that we're moving the vector in such a way that its covariant derivative vanishes. So that's what we mean by parallel transport. So parallel transport is you move the vector so its covariant derivative vanishes. So if you think of it as a contravariant vector, you want its covariant derivative to vanish. If we write it in terms of covariant components, then it's E lower I dot dv should vanish. And so we have v comma L here, but v is this thing that's the scalar, that's the invariant form. And we differentiate, we get this. now, and the dot product of VI with that gives us a Kronecker delta minus a Christoffel symbol. So once again, the covariant derivative of the vector vanishes when you parallel transport it in along the sphere. So if the curve we're talking about is XL of U, so that's the curve going, say, going up the surface of the sphere from the equator to the North Pole, then the conditions for parallel transport are that dv du, which is then partial dvi du, partial vi, partial xl times dxl du, well, that has to be minus the gamma multiplied into vk dxl. So the covariant derivative vanishes, or equivalently, the youth derivative of the ith component of v is, which is this, has to equal that, so that the covariant derivative vanishes. So these are the mathematical formulas that relate to parallel transport. And now I think we're kind of getting to the end of the mathematical basis for general relativity, because now that we see what parallel transport is, and we've rehearsed or gone through what covariant derivatives are 3 or 4 times, it's said that repeating things is a way of teaching things. Some people warn that repeating things is a way of convincing people of things that are actually not true. But let's leave that aside for the moment. Anyway, to find the curvature at a point, what we're going to do is we're going to parallel transport a vector around a curve that runs a tiny square about the point. And then we're going to measure the change in the vector. Now, when we did that in using 3-dimensional spaces, the embedding space and the physical points as being the points on the surface of a sphere, we saw that here we just did a triangle, but this time we're going to do a square. And so we want to know what is the change in the vector as we run around the square by parallel transport. Well, remember what parallel transport is. Let's just remember that in parallel transport, the contravariant or covariant components of the vector transform this way. And so the question is, if we integrate this, or equivalently this, around a little square, how big a change do we have in these components? Here on the sphere, we found that when we went up and then down and then over, we got a change of 90 degrees. So let's see what happens in general. So in general, then, what we do is we integrate gamma. The change in the component, in the covariant component, is the Christoffel symbol times the covariant component times the distance that you go. And on this curve, we're going to approximate all this. We're going to approximate the affine connection as the affine connection at the center plus the derivative of the affine connection times the distance you are on the square. So in other words, we're talking about a little square here. And we've got the center of the square here, and the affine connection here is basically gamma 0, and then over here or here or here. For example, right here, it's gamma 0 plus the derivative of gamma with respect to, if this is x, then this might be the one direction times dx1, but dx1 over 2, because we've only gone half the distance of the square. Anyway, this is what the Christoffel symbol of the second kind. Well, why don't I just call it the gamma symbol? What the gamma symbol is, it's the gamma symbol at the center plus the derivatives times the departure from the center as you go around the square. And this covariant vector, well, it's the value of the covariant vector at the center, and along the square, the edge of the square, it's the derivative evaluated at the center times the distance. And so what we are going to say here is that Vn, we're going to set equal to gamma times V. That is to say, that's this equation here. dV du is gamma V times the change in distance. Okay. So we're using those formulas of parallel transport to compute this integral along the square. I'm going to throw away anything of second order because this is a physics department. So we keep only terms linear in x minus x0 because x minus x0 never gets bigger than some infinitesimal quantity. And so this integral then is what? Well, it's the values at the center times this actual integral here. I'm a little puzzled that it became quite that simple. I'm surprised there isn't some derivative in here somewhere. Well, anyway, let's just go with that. So in other words, what we've got here is gamma times V. All right, so gamma times V, and so you've got the gamma plus a derivative times that, and then you've got V plus a gamma times a V times that. And when you multiply them together, what you're left with to lowest order is just, it has to be linear in x minus x0. This just means the nth component. It doesn't mean the power n. And now this integral along here, if the side is a blank, if the square is a by a, then this integral is going to be a squared, is going to be plus or minus a squared. And if this epsilon is -1 if the two are, in other words, epsilon 1, 2 is 1, epsilon 2, 1 is -1, epsilon 1, 1 is 0, and so forth. So that's what this is if you work that out. And so this dvi then here, here are these derivatives. That's right. I wondered where the hell the derivative terms were, and they're right here. So this is the derivative term. Anyway, so what is this thing? Well, it turns out to be VK times, in other words, this thing here gives, with this integral being a squared times plus or minus 1, and then you've got a VK. So you've got the change in VI is A squared times this bracket thing that's linear and quadratic in the gammas times VK. This thing is Riemann's curvature tensor. So the curvature tensor is what you get when you parallel transport around the square. And so it's a measure of curvature. And what we can see here is that it is quadratic in the gammas and linear in their derivatives. And you can also see that it's antisymmetric in L and N, obviously here, and a little less obviously, but equally obviously there. So it's antisymmetric in two indices. This is something that has 4 to the 4th components. So 4 squared is 16. 16 times 16 is, I guess it's 256. So that's a lot of components, 256 components, but it has all these symmetries. So it doesn't have 256 independent components. Let me just see if I wrote down what the actual number of, right. The total number of independent components is 20. So not 256, but only 20. And now this is so important. I think I should write this thing, at least sketch it a little better. So let me go to red here and try to write this down. So we're integrating around the square, and we're doing gamma KIL VK dxl. All right, so let's look at what the gamma was. The gamma was, so what's gamma? It's gamma 0 plus a derivative, an nth derivative of gamma times x minus x0 to the nth. And then it's this VK. So let me write down the VK. That's VK 0. Because gamma has 3 indices, but I'm going to, well, all right, I'll put them in maybe. It's K and then IL. All right, hold on. I'm going to have to use the eraser a little bit then, because IL and then 0. I'll put the 0 up there. And this is VK 0 plus, and then a gamma, again, a gamma 0 times a V 0 times an x minus x0. And again, I have n, but I don't think I should have n there, so I'm going to just say m. Whoops. Just say, well, m. And then dxl. So what we expect here then is we're going to have the gamma. Let me just make sure I've got this right. Okay. So what we have here then is we're going to have a gamma 0 times a VK 0. And that is just going to cancel because the integral of dxl around the square just gives us 0. So integral dxl. And then we have a gamma derivative, whoops, a gamma derivative times an x minus x0 to the n, say, then a VK 0, and an integral, again, dxl. So what I've done there then is So I've just done, in other words, this term times this term gives me that term. Then if I go to blue, what I had was this term times that term gives us the blue thing. And then we have the integral where we have, let me go to, let's see, yellow. Then we're going to have this gamma times this. So we're going to have gamma k, another gamma, and then a v, and then an x minus x0 dxl. Now, this one term is 0, so this term is 0. So we have these two terms left over, and these two terms are a derivative of a gamma, and then something that's proportional to two gammas and a v. And of course, the derivative term also has a v. Okay, so this, so I've sort of derived this in that way. And if we now imagine, if we now do this sum over n and L using this expression here, what we get is this formula for the change in the ith covariant component. And the thing in the brackets then is the thing that tells us how much that covariant component changes when we go around a tiny square, if we're following the points on some surface in some higher dimensional space, or some curves. It could be a two-dimensional surface in just ordinary three-dimensional space. Whatever it is, this is how much the thing changes. And this is what's called the curvature. And this thing with four indices is Riemann's curvature tensor. And as I said, it has formally 256 components, but it has so much symmetry that there are only 20 independent components. And different people use different sign conventions. I'm following the crowd. Weinberg, unfortunately, uses a different sign, and he's probably made the right choice because Weinberg was so very smart. It's very sad to have to use the past tense with Weinberg. I didn't know him well, but I sort of knew him, met him many, many times, and sat in some of his lectures. He was a remarkable person, absolutely. Anyway, there are these various symmetries. I think I'll just say what they are. It's antisymmetric in L and N, the last two indices. You can, to get the covariant, well, the thing comes out with one upper and three lower indices. That's because the Christoffel symbol of the second kind has one upper index and two lower indices, and then we differentiate, so we get a third lower index. And then, so it has this form, but you can then use the metric tensor to lower one of the indices, and then you've got something that has four lower indices. So it's a covariant tensor of rank 4. And it turns out that it's also symmetric in the last two indices, well, obviously. And it turns out that you can think of it as the commutator as a commutator. All right, let me just give you the punchline. You take two covariant derivatives, take the commutator acting on VI, and what you get is the the Riemann curvature tensor multiplied onto VK. So this Riemann curvature tensor is effectively the commutator of two covariant derivatives. Commutator, as you know, is so A comma B is AB minus BA. That's the commutator. The anti-commutator is AB like this, and it's AB plus BA. So we're talking anti-commutator here. You can think of the Christoffel symbol as a matrix. You can then write this in kind of a matrixy way. So there's something called Riemann normal coordinates. In Riemann normal coordinates, what you have is that the derivatives of the metric vanish at x, so at a particular point. So then if the derivatives of the metric vanish, then the formulas for the gammas vanish, and then the curvature tensor is just the derivatives of the Christoffel symbols. By the way, this is the Christoffel symbol of the first kind, with all the indexes lower. And it then is this expression involving second derivatives of the metric. So remember, in Riemann normal coordinates, at the point, you've got all the first derivatives vanishing. So in these coordinates, this thing is antisymmetric in its first two indexes and symmetric under the interchange of the first and second pairs. Anyway, I don't know. I think we can sort of skip that, at least today. I skipped the Cartan thing, so I don't want to go through that at the moment. Oh, well, not only haven't I skipped it, didn't I skip it? I haven't anywhere near it. So I think I'm going to skip that. You can just, there are various ways of deriving the other symmetries. Let me say what the Riemann tensor, the Ricci tensor is. You take the Riemann tensor, and then you contract it. You set the upper index equal to the middle lower index and sum, and that gives you the Riemann tensor, a Ricci tensor. And if you then do a further contraction, you take the Ricci tensor and you multiply by the inverse metric tensor and contract over both indexes, you get a scalar, and that's called the curvature scalar. So this gives you this is what we typically mean by curvature, or the curvature at a point. And so in particular, if we look at the curvature of the sphere, well, let's see, we're actually out of time, so I think I won't keep people any further today, because we've gone through an awful lot of stuff. I think we're essentially through most of the mathematics behind general relativity. I'm just flipping through here to see what else we'd be well, maximally symmetric spaces, principle of equivalence, tetrads, scalar densities, yeah, that's something we need to do. Covariant Laplacian, equations of motion, weak static fields, that's important, time dilation. Well, there are all kinds of juicy things that we need to do before we get to finally the action of, the action involves the Riemann scalar, or the curvature scalar. And so the action of the gravitational field is the integral over all of space-time the square root of the absolute value of the determinant of the metric, that times d4th x gives you something that's coordinate invariant, and then the scalar, which is coordinate invariant, generally covariant or invariant under transformations. And so that gives us an action that's totally invariant, independent of coordinates, and that's the right action then. And that then is what gives us the Einstein's equations. If we add to the action of the matter fields, we then get Einstein's equations. Well, all right, I think that's enough for sure for today. I don't see any questions in the chat box, and so I'll just wish you all a weekend, a nice weekend, and a safe weekend. There's a colloquium which will is an in-person colloquium given by someone who was a graduate student here not long ago, and he did a thesis with Keith Lidke on biophysics, and then wound up being a professor at Yale, doing biophysics, and so he'll be talking to us. It's in person at 3:30 in room 1100 in Pais, and for those who want to watch it remotely, then it'll be broadcast via Zoom, and the password as usual is PANDA, which is capital P, lower AND, capital A. 40 years ago, the country was fascinated by pandas, and one of the physics department secretaries realized that physics and astronomy could be abbreviated by PANDA, and so that has stuck with us ever since. I've regretted it every moment, every second of every day. I think it's kind of silly, but anyway. All right, have a great weekend. Goodbye, everybody.